So there are any questions? So start again on this notebook. We started to analyze this morning. The idea was to restructure the Einstein fit function that we analyzed this morning in a way that it is more structured, readable, maintainable, possibly bug-free, and generalized. So we are working on this idea of having classes as a thing organized as classes. So there is this Einstein class. During the lunchtime, I modify a little bit my classes to add some few new methods. For instance, I define in Einstein class the set APFU method that can allow you to change the number of items per unit formula in the attribute that stores the number. And even in this class here, I define a function to get the name, to get the number for item for formula units, which is being read from the file. So in the data class, I add this function here, and also the class also store an attribute which is used to make plots of the CV for the specific heat with respect to the temperature. It was initialized to the value 100, so 100 point in temperature. And but if you wish, you can change the number of points of making the plot by using this function, this method, set and plot, and so on, so on. So this morning we already see how this class, what are the attributes and what are the method that this class incorporates. Then I call the Einstein class. So I will put I create an instance of this class, and the instance is called Ein. Then I also create an instance of the plot class, and I will put my instance in the variable myPlot. And then I define here the function Einstein fit that should be compared with the function which I defined this morning this way. So this function making too many things in one time, one shot. And you see that this, as I already told you this morning, we have a lot of input parameters, also arguments to work with this function. Now Einstein fits in the revised version just take two arguments. Name, which will be the name of the phase, of the mineral phase, of the material that we are using to analyze it, the specific heat as a function of temperature, so just the name of the phase, and the model. One parameter Einstein formula, or two parameters Einstein formula, as is we provide a default for the model variable, which is 1. So if I do not provide a keyword model, the model will be the model with one parameter only. And if I write model equal to 2, I will get a 2 parameter model. So only 2 arguments instead of many. And the understanding of these parameters is quite clear. They talk about themselves. I have a name, so a name of the phase, a name of the system I'm working on, and the model I will use. Then the Einstein fit will require the setting of the item per formula unique parameter. So I will use the method set APFU of the Einstein class. And so this method will accept as input the number of item formula unit, which can be read by the function, by the method get APFU of the data class, so of the data, this class here, of the data class. So this class will store this number, and the store is retrieved by writing name dot get APFU, and this name is set in the Einstein function class, in the Einstein instance of the Einstein function class, by using this method here. Then also there is this guess equal name guess, bounds equal to name bounds. They also are attributes of our data class. You see this initial guess set to 50. We have these bounds set to 10, 200, 2,500. If you want to work on this example by yourself, by extending it, you can provide method for setting this value here. So just not change directly the value of the attribute by saying name dot guess equal to some number, but name dot set guess, and then you provide the number as an argument, exactly in the same way which is done here. So where I set the number of item per formula unit by using no, this is get. I set the number of pointer plot by using the function the set plot. So you can do that yourself. You can add this method and use them to set some different parameter for guess and for bounds. And you can also add functions, method, for instance, get guess, get bounds by two other methods that you can store in the data class class. So now this has been done here. Then the Einstein fit function looks at the model parameter. If this model is equal to 1, it will execute the card fit with the function containing only one Einstein temperature to be refined. If model equal to 2, the function will be the Einstein 2 fun, and so you will obtain back the results of the Einstein temperature defined. Then if model equal to 1, you will have the printing of this simple parameter, one single parameter here, defined, and else, if model is not equal to 1, that is, it is equal to 2, then it will print this one. Even here you can add something. For instance, what if one user, instead of calling Einstein fit with model equal to 1 or model equal to 2, will call the fit with model equal to 3. Then you can add some code to say, all right, if model is greater than 2, set model equal to 2, for instance, and print a message. There is no method there is no function with 3 Einstein temperature parameters. So the number of the Einstein temperatures has been decreased from 3 to 2. So some protection against bad use of the function. So if the user try to make computation by using methods which are not implemented, then the function returns some error and say that or some warning and say that okay, you can work only with model 1 or 2. Then if the model is equal to 1, the attribute in the name class in this name, which is the instance of the data class, some attribute will be changed. So the name model will be equal to 1, the name fit 1 will contain the Einstein temperature computed, the relevant flag will be set to true, else if model equal to 2, something else is written in our in our attribute. So these attributes and these, in particular, the Einstein temperature will be saved in the data class, in the instance of the data class. And you can do the same for instance, the uncertainty for covariance matrix, which is saved here in this variable fcov. You can foresee the existence of some other attribute that stores the value of the uncertainty of the coefficient that you refine, and you can save them as attribute of the class. So you can retrieve those value after, even when the function ends. Okay, that is the Einstein fit function. Very, very simple. It's not that simple, but anyway, it is simple compared to the function that we defined this morning, which was quite large. Then to plot the fit, there is a particular function, this plot fit, we accept name as argument, name of the phase. Then we'll define a t-plot range, so a number of temperature from the minimum temperature that we set, the maximum temperature that we set, and the number of points that we want. You see all these variable min x, max x, and plot are prefixed with name dot. That means that they are attribute of the class. They can be changed in the class and so on using the appropriate method. Then the array V1 plot and CV2 plot will be computed by using our functions here. And then we create a series, name x, dplot, and name y, CV1 plot, CV2 plot, just to make this plot here by using the multi method of the myPlot class. Now you can change this plot fit, because this plot fit is intended to be used in the compare fit function that compute the Einstein fit in the two cases, with the model equal to 1 and the model equal to 2. So when you use the function compare fit, automatically the parameters for the Einstein with one parameter, Einstein function with one parameter, and the Einstein function with two parameters are computed. And so you have all the data you need to make the multiplot. But imagine that you want to use plot fit function without passing from compare fit function. It is not sure that you have calculated that you have the parameter for both the function, Einstein function and Einstein 2 function. And so you should protect your execution here by putting some conditional evaluations of if you only compute the fit for the Einstein fun, then plot the data for this function only and not the data for the other functions. Otherwise, if you compute only with the two-parameter function, do not compute this line here, because you don't have the parameter for the Einstein function with one single parameter. If you don't compute nothing at all, then you should return, this function should return a warning, say that you must first make the fit by using the function Einstein fit, and then you can plot the results. Okay, now this is compare fit. If this make a check, if you already compute the fit, then you will find that the fit flag, which is a Boolean that we define in the data class, for instance, is false. If you don't compute the fit for the Einstein with one parameter only, the Einstein 1, then this will be false. This variable here will be false. Not false will be true, and so this function is executed. So the Einstein fit function will be executed, and the model will be calculated, will be refined. The same for the other flag, the second flag. If you never compute before the fit for the Einstein 2 function, then this flag will be false. So not not false will be true and will be executed, even this other fit, by using the model equal to. So this is the meaning of this one is that if you already compute the fit and you want to compare fit, you just want to compare fit function on data that you already defined before, already computed before, it is not necessary to uh, re-execute again the fit because they are already done. All the results are already stored in the attribute of the data class. So it is not necessary to recompute the fit. Of course, you can do a lot of other things. For instance, you say, all right, but be sure, because I changed something in my data set, I want to force the system to remake the fit. So you can add some keyword argument here. For instance, you can write force um, with the default equal to false. And you can call your compare fit function, for instance, by specifying an argument which could be different from false here, but could be true. In that case, you can add here some more tests to say, okay, if false is equal true, do the Einstein fit um, with one function, with the Einstein one function, or with the Einstein two function, according to the model selected, even if they are already calculated, if they are already present in my system, because I force you to make the calculation, so you can act in this way. So this function compare fit as all the other function behind can be changed. You can add many other possibilities, adding keywords, adding printing. So you have the possibility to change it as you want, just as a matter of exercise. So you should try by yourself to make this modification. Then there is a simple printer. This printer with double apices without nothing just will print a blank new line. Can be useful for aesthetical reasons. Then you calculate the specific heat with model one with Einstein one function or Einstein two function by using list comprehension for the temperature that you have in your data file, and then you, as done before in the previous notebook, you calculate your series, you make the data frame for your series, you transpose your data frame, and you print out the table of the data. And if plot here is equal to true, is one argument of the function. If plot is true, then plot fit, then call the function plot fit with this name here and make the plot. Otherwise, just print the table of numbers and the CV is a function of temperature, and you don't make any plot. Now, all this section above are just definition of classes and functions. You have just these two direct execution, that create the instance of the classes, aim and my plot for making the plot, and then you use it. So above, all in the cell above are just definition. Then use it. Here there is just a setting of a parameter which are used by the plot function to get a plot made with some specification concerning the size, the font, and so on, resolution, if you want to save or not your plot in some files, graphic files, and so on. So just an instruction to set some parameter. Then create an instance of the data class, which you will call py, this for pyrop, with the name pyrop, and you will write here the name between apices, the name of the data files, and here you specify here the number of atom per formula units. Then read the file py read is the method of the class py. Read the data files. This is not the name of the data file. This is now the name of the path. Probably one could change that because you see that we define it above in the class. Oh, this was the path here. Data file. Okay, data file. All right, the data file. So read data file. Go on. That's default. Okay. Yes, it's okay. Read the data file. Where is it? Here. This is the path used. So the function read accepts one argument, and the argument is the path on the disk where the file has to be found. The file with name cvdata.dat. And the function read accepts the path. And in fact, my files here is in the folder data files. Then print some information about my data set with py info. So I execute all the cell above because I didn't before to define my functions, compare fit, and so on. Now I do that. Now I execute this cell, so this cell set this parameter, define here the instance of the data class, call it py, then read the files, then print py info. So use the method info to get information about our data set. And you see that data set name is Spirop, is the name which I assigned it here. It is written here. Dataset file is this one. The number 8 of formal unit is 20. Then in the file, there are 20 different temperature points. There are 20 here. The minimum and maximum temperature are 20 and 700. And fitting model, no. For now, there is no any fitting done, so the fitting model is no. Then we compute the fits with the tool by using the compare fit function. Okay, run. Okay, that's done. Compute the fit, and also you have your plot here. Now I want to use the representation class, the print py. We'll use the Dender magic function wrap in the data class that will print information concerning our pyrop, our instance of the class data class. So I print this one, and you see what we have: the same information as before here, but now for fitting model, instead of having just known, we have this information. So one temperature model, ISO temperature is this value here, and with the two temperature model, the ISO temperature refined are this one. Now, you want to select an either temperature, you want to start to make the fit not from a minimum temperature 20 Kelvin up to 700. You want to start from 300 Kelvin. So select will accept 300 as a possible argument, which is the minimum temperature to select. So I will start to select data from 300 Kelvin on. So I write pi select 300 and I remake the compare fit. So just to and if I want, okay, you have your fit. Of course, if I write, for instance, pi info or print pi, I have my information here. So the input parameters at the beginning are just the same. The number of T points is 20. The original temperature range was restricted to 300, 700 Kelvin. So the fit will be done in this region here. And, and so I don't have any temperature which is exactly 300 Kelvin in my data set. But I have a temperature starting from 306 to 700 Kelvin in my data set. So it will print here the minimum and maximum temperature that we have. Should be in agreement with this interval I choose. Then the one temperature model is this one. And the two temperature model gives us this value that you can compare the values that we obtained above with the whole set, and they are a little bit different. And here are the plots. So you can change as you wish your this this these classes. So you can add new methods, and they can do something else. Okay, this is a good structure of your programs. It's not the best structure you can imagine, but anyway, it's already a good structure. Then another point is that you see that imagine that you are a user, not just a developer of the program, and you are a user of the program, and you are not really interested in knowing how the program works. You just are interested in getting results. So using this compare fit function for some data, making plots, getting the numbers, but you are not interested in knowing how the program works. So in this case, of course, you can simply ignore all the cells written above, but anyway, they are there. And that if you are not a developer, um, it would be better not to have the code written on your notebook, on your cell here, because there's always the possibility that you, by accidentally going some cell, um, type something. So means you delete a character here, and your Boltzmann constant becomes a very large number to compare to it was before. And of course, you will get crazy results. So your cell should be protected on your cell defining the function of the class should be protected against the possibility that someone typing something which is wrong. So what you can do, you can define a file. For instance, I wrote here on my file here in the which I call Einstein underscore fit.py. So not a notebook, but just a Python file in which I write all my imported library. So import and Python P. So everything which was written in the either of this notebook here. It is reported here. I import also my plot function. Then I define all the classes here inside. The two classes I defined. I also create here inside the instance of those classes that I want to use. Then the functions I created. And all is contained in this unique file. Might be that you can also separate in two files of the material. So you can, for instance, imagine to have a file just containing the classes and another file just containing the functions. That's a possible another possibility. So all the functions which are defined outside any classes, that's Einstein fit, plot fit, compare fit, and so on, they can be stored in some other file. So you will have two files in that case, and you will know if you have to change something, if you have to modify. You know that if you want to modify a class, you will go in the files that contain the classes. If you want to modify your function, you will go in another file. So things will be better organized on your disks. And when you load one file, you load a specific file containing some information that you already know it is inside. But anyway, you have in this case you have this file, and so you can think to another Jupyter notebook here that's intended for users where there are no longer any class and function definition. You just see what you need to make the computation. And so you have to import anyway the file which is Einstein fit.py must be imported in your notebook, and you can do in several ways. I use this notation here from Einstein fit, Einstein underscore fit, import star. This method works with the star in particular, will import everything from your file, from the einsteinfit.py module. Everything will be imported. Not You can import all single function, single method, single class by using a name here. So I want to import only compare fit. I would write compare fit. So only this function will be imported. But otherwise, you write import all. In this case, this is an import statement is different from this other one. I already discussed this morning, but I redo here. Einstein fit. You can specify an alias, for instance, as fit, for instance. Now, if you import in this way and not in this way, every time you use a function or a class which is contained in this file here, in this model here, you have to prefix fit dot. So I want to use, I want to read data, I should write fit read. So I have py is the name of the instance of the classes, data classes I created here. Also here I have to write fit data class, fit, and so on. So every function and class that is present in the Einstein fit should be addressed with this fit prefix. But if you import in this other way, then it is not necessary. So you can write this one. This is not advised anyway. So I tell you that you can do that, but this is not advised. It is advised generally only for small modules. So and for small program that you don't make confusion between classes or function that can be defined differently in different module that you load. Imagine that, for instance, we have seen, for instance, imagine that you have a Python function that computes the square root of a number. It exists. And you also have a numpy function that computes the square root of the number. And imagine that you import Imagine that you import numpy with the star. From numpy, import stars. Then if you want to compute the square root, then in that case of a number, so I just write, otherwise it becomes 2. Okay, Python 3. So I opened just a new notebook just for testing. So imagine that you import numpy, or better, from numpy, import star. Okay, you can do that. Now imagine that you have you want to compute the square root of a number. In this case, you will write square root as sqrt and the number, for instance, 2. It works. Okay, but what I'm using here, the square root function from numpy or the square root function from Python. So I don't know if indeed Python has a square root function defined. Maybe yeah, maybe not. I'm not sure of that. But if it exists, then you don't know. The interpreter knows, because it's as in terms of standard internal default that probably you will choose some square root function, but you don't know what is it. Much better is to work this way. Import numpy as np. Now I clear the kernel. Okay. I import this in this way. Now I run this one. Okay. You see now that there is not actually an sqrt function for Python. Now what you are doing here is write compute the square root function of 2. with a function. Now, it does not exist in the Python environment, a square root function. But if it were, then you will compute the number 2 by using the square root function Python. In this case, you get an error because square root is not defined. You have to use NP. You want to use the numpy square root function, and now you get a number. So you see the difference. In this case, you have to specify NP. In the other case, you have not to specify nothing. You don't specify nothing. But in that case, you are not clearly sure of what function you are using to make your computation. As a function, a basic function in Python, as a function or some libraries. So in this case, if I write Einstein fit import star, I can write all my definition, all my function and attribute and so on, without specifying any alias and the dot. I can do that because right, my module is small, and so there is no possibility of error or confusion. And you can write shorter expression without having to use any prefix. But take into account that there is this danger always. Now, I import my Einstein fit file, my Einstein fit module. You see, this module already has some import defined inside. So when you import this module, you also import automatically NumPy, Pandas, Matplotlib, SciPyOptimize, and Plot. They are all imported when you import Einstein fit. So all the imports that are found in Einstein fit are also imported in this Jupyter notebook. So you don't have to import them again. They are already loaded. Then I used my plot set param, so I define my parameters here for the plotting. Then I read data from disk concerning Pyrop and Quartz. I have two phases now, not just one, and I assign these two phases to two different instances of the data class. Then I want information read for the Pyrop, and I want information read for the Quartz. So I run this. Okay, so these are the information printed by this py info for Pyrop. This is the files, number of point, temperature point for Pyrop. And for Quartz, you have another data set, you assign a different name. The number of atoms for uniform is 3, SiO2 is 3 atoms. You have 30 points, not 20, and the temperature range are from 20 to 650, so there's a different temperature range. But none of this data for Pyrop and Quartz has been already computed, so there's no fitting down. Now I want compare fit for Pyrop. Don't want the fit for Quartz. I will write compare fit for Pyrop, and you have the results. Okay, for the two models. You see that the Einstein function with only one parameter is not behaving very well. Then you try to reselect the temperature. So the minimum temperature will be 300 Kelvin. Recompute the fit. Now it's better. We already did it in the previous notebook. You have the same results. Now you want to do the same computation for Quartz. So you write here your compare fit with Qt. Qt was the name assigned to your instance of the data class. Qt equal data class for Quartz. And so you have immediately the computation for Quartz. The one fit function, the one parameter function will work very badly if in case of Quartz. In the low temperature region, you also have some deviation of the two parameter function with respect to the experimental data. Anyway, you can Qt select 300 Kelvin, compare feet, and so on. Anyway, you see that the two parameter function works well with your data. There is some discrepancy, a higher temperature, and the one parameter Einstein function is not very good. Anyway, you have here your information. If you want to retrieve information for pi you already calculated, you don't have to compute, just write pi info, and you will see what happened here. You have your information concerning mixing temperature for one model, two models, and so on. The selected temperature range. So you can do that for as many phases you want at one shot. Just define the data class, just define the instance of the data class accordingly. You will have your data files on your disk, and then you can compute them and compare them. So it's much flexible. Otherwise, in the first instance of this notebook, with this Einstein fit function, every time you want to get back the information concerning the fit of the Einstein temperatures defined by the fit, you have to recompute them by using this function here with all these strange parameters and so on. So it's very messy. In this case, very neat. And what you don't see, it's important for an end user, is you don't see the code. You just see what's the final result. So in the function that you have to use to make computations. Okay, questions? No questions? Everything is clear? Okay.
I
Yeah.
was wondering, since one of the problem in the previous version of the function was that it had too many arguments, couldn't we import these arguments from an external file, like a sort of configuration file where we set
Yes. You can, for instance, if you know that you have some parameters to be defined, and there may be many, you can write a class that reads this file and will store all these parameters as attribute of the class. Then they are used by the function you define. So you don't have to go in the function and set manually the parameter or pass you have not to pass this parameter as argument of the functions, but you can define a class and store the parameter there. So they can be read from the file, but then they are stored permanently in your session as attribute of the class. And then you can add to your class the method that are necessary, for instance, to reset these parameters. So in the file, you have parameters that control the number of points for making a plot, and it is 100. Well, okay, you can define a function which is for instance, set number of points, and you can reset the number of points as the value you want. So if you want, within your program, you want to change a parameter that could be a default, you can change it anyway by using this default. Another possibility is to define a file containing constants. And the .py file, so just a normal Python files, which contains some numbers stored in some variables, and you can import the file as you import any other files containing classes and functions. You just can import a file that just contains assignment of numbers to variables. For instance, I did it. Now I show you. You could find rapidly. Okay. Okay. In the project I'm writing here, I have this parame.py file. Sorry, okay, tries to, okay, it's here. No? You see, I have this parameter file contain just some attribution. I also write a lot of comment explaining what these parameters are. And this file is imported. If I open, okay, PM3, I have to look up Python file now. Okay. You see here, import parame SPR. So I import in my program here these parameter files, and I can access all these value here, delta, numpy, and so on, by using the PR prefix. So if I, for instance, if I search here for PR dot, you see there are many points. All these gray lines indicate where you find this PR dot. PR.kt, PR.kt, so these are all points, these are all value which are stored in this parameter file. So you can import constant in this way. That could be a good way. But generally, now this was the first thing I did when I started to write my project. And then I abandoned it. So now, for historical reason, and my project has more than 2 years. For historical reason, I kept this file here, is working, it is used. But then for other parameters, I define classes that can define for other function and can change the value by using appropriate methods. So method to set parameters and method to get parameters. In this way, you can have functions that do not require a lot of parameters as input, so not so many arguments, because all the other parameters are read from the classes, from the variable stored as attribute of classes.
Okay, thanks.
Okay. Okay, so this thing fits. Okay. Now, I will show you another notebook, not advanced matplotlib. I will not go in detail of this notebook. I want just to show you something, some advanced facilities of the matplotlib libraries can also make three-dimensional plot and working with it. So this is one of this function. The function I will use are those magic functions that do wonderful things. The point, as I told you this morning, the point of this course is not showing incredible things that our function can do, but the point of the course is to learn how to program in Python language, or in any language if you want. So anyway, I'll try. I use this notebook, reset the kernel. So I import my libraries, and also I import the new libraries here. MPL toolkits, import mplot3d. This function here, this class here, that belongs to this class, or the class here, will make 3D plot. And we'll start by defining a function z of x and y. So this is a function of two independent variables. And I can create a measure point. So now I run the cell. A measure point in the x and y plane. And I want this point to be 40 points on the x-axis, 40 points on the y-axis. So I call these two parameters 40, so mpx and mpy. They are set to 4. And I want domains along the x and the y-axis. So my x variable should be comprised between -2 and 2, and the yr should be comprised between -2 and 2 also. Then I create vectors or array of the x and y independent variable by using the link space function. So from xr0 to xr1, and this value of these two elements here of the xr just -2 or 2, and px is 40, so it will create a list, an array of floating point number from -2 to 2, and there are 40 numbers this type, the same for y. Then I define a grid, a mesh grid. It will show you now the grid in a moment by using this function mesh grid that use this function, this value xy created here. The total number of the grid will be the product of npx and npy, so 40, 40 times 40, 1,600 points. Then I can also reshape all the points. This is I get in this grid here. I can reshape as one-dimensional array for future uses. I make run here just to plot the grid to show you the grid I get here in this. Okay, this is the grid. You see that I have the x axis, the y-axis, and they go both from -2 to 2, -1, -2 to 2 for the x-axis, -2 to 2 for the y-axis. So this mesh grid function here, which is used here, will create this mesh, this grid here. Then I want to compute a z function. So I have this my function of x and y, and for each value of x and y, so for each value of the two independent variable, compute z in this way. So you initialize z to 0. Then for IP in range LP, what is this LP? Is the length of C, and length of C, so is this list here, list of coefficient of a function that's just simply a function of containing power. So I will say what is it. This is x to the fourth times y to the 0, so just x to the 4, plus y to the 4. This term here corresponds to x to the square x. This corresponds to this square y. This corresponds to x and y, so x times y. This is just simply x. This is simply y, and this is a constant. So these are the power of each term in x and y of our function z, and each of this term is multiplied by a coefficient, which will be 0.2, 0.4, 1, minus 0.5, and so on. So this function will write 0.2 times x to the fourth plus 0.4 times y to the fourth plus 1 x squared minus 1.5 y squared plus 0.5 times x times y. Then the term 1, 0 will be simply 0 because there is a coefficient in front of it, which is 0. Then you have 0.2 times y minus 0.8. So this is a function of powers of x and y up to the power 4. Now I'll go through, I compute here a list of integer value range LP, where LP is the length of this list here. So how many terms I have in my functions. And I compute the value of z by multiplying my coefficient found inside this list times the x to the power, which is defined by this PW list here, a list of tuples, and so on. Then return z. Okay, this was already computed. Okay, so now I can go on and plot figure where I compute the figure by using scatter point. So we will see what is the aspect of this figure, scatter 3D, and I provide here the x and y and the z values, the computed z values, and I set some label and so on, and this is what you get. So you use this your x-axis, y-axis, and on these other axis here you have the z. So you have the surface drawn by this function here. Now one can say, all right, good, but not satisfied with the view. So the perspective, the angles, and I can write, um, I can use this method, view init, in which I can define two angles for rotating this figure. I choose these two values, just random value, and I can redraw the figure. So I have another view of this function, the same function viewed along different angle. These are a scatter representation, so each point is represented by just single point, but maybe that I want a surface, something which is more close to a surface, so I will use the function plot surface. This is what you get. Of course, you can change whatever you want. You can change the color of the axis, the labels. Everything can be changed and customized. Or maybe you are interested to see contours levels. So I will use these other methods here, contour 3D. As you run the code, you get this representation, your surface, where you see clearly the contours level. You have a settle point here. You have two minima around this region here. You can also, if you want, change the view by using the same. I didn't now, but we're using the same view init function, so you can do what you want almost. Now you say, all right, contours level are very nice to see in 3D, but I want to see this contour level in two plots. So I will make a projection, this contour level of a plane, the XY plane. And so you can write this little function here, which use the contour method. You run it, and you get this one. So you have a representation of your contour level, and you can put, as is inside here, you can put in the number that define each contour level. There's an inline equal truth with some font size and so on. Put the x, y, and axis label, put the title, and so on. Of course, even these figures is fully customizable. You can also change the colors in this way. Now this is simply default. And now something more interesting. This is just a graphical representation on something. And you could be interested in getting the XY value along some particular contour level. So, first of all, I modify a little bit this drawing just for technical reason. I will explain why in a moment, but just I redo this picture in which I specify inline equal to false, whereas before it was inline equal to true. And you see that when I write inline equal to true, the numbers here is interrupt the line of the contour levels to make room for writing the number. In this case, no, you have the contour level with the value, but this value is superimposed on the line, in this case, and also in this other case. So there is no room, there's no interruption in the line by the label. That is a technical computation, because if you are in the situation you want to, for instance, to retrieve the value of the xy coordinate for which you have this contour line, the number that you get as the end of the procedure will be interrupted in the position where you find the label. So you have a gap in your file, in your data that you will recover, because the labels are written in this way. If you write the labels in this way, just superimpose on the line, you don't have interruption. So just not very nice representation, because you have this nasty uh, way of representing the label, just superimpose the line, but more useful if you want to get the value. Now I write here the function which is the extract values. I call it extract values for a given level. So this function expect that you provide a level, and then there are some magical command here with magical method that is con collection get paths. Con collection get paths lab. So I can this function con collection expect as an input is not an input is expect an index that will indicate the level that we want to choose according to the value of the label, and we'll get the path. So we'll get essentially an information that is related to the xy point that gives some lines here. Then I can I don't explain now what is this left side pretorder because I do this. I will. It is not that complicated. Just technical information that you will not remember. As I don't remember when now I remember what is doing because I prepared this notebook not much time ago. But I'm sure that within a couple of weeks, if I want to redo something similar, I have to read the documentation again because I can't remember all this stuff. So at the end of the day, what you get is a set of numbers along your path, set of coordinates x and y that I can plot again. And so I run this function, and then I want to extract my values for the contour level having the value 0. So 0, it's not contour level. Okay, here. I have this level 0 for the first level. So for the level having the value minus 1.5, which is around this inside. So you see that you have a positive number of the z function here, then you have the 0, then you have your contour level becomes negative, and minus 1.5 is more or less in this region here, for here and for here. So with the extract, I will have this set of xy numbers. If you want to be sure that the contour level is really have the value minus 1.5, you can compute the function z with the x and the y ranging in the path that I have extracted, and you see that okay, this is a numerical an extraction from this of this value x and y, which is a numerical computation. It has some precision, which is not very high. It depends also by the resolution of the grid that you define. Now I wanted 40 point here on the x-axis and 40 point on the y-axis, so the resolution is not that high. So I cannot expect to have contour level very precisely defined. But anyway, the value of z are almost all in the very close to minus 1.5. That is what I wanted. And these are the x and y variable. I can also import now these pandas libraries, and I can also construct a data frame with this value which I retrieved, and I can save the data, the path, on the Excel on an Excel file. And so if I go in my folder file, there should be in data file, I'm already there, data XLS is this one, and these are my value of the xy variable which correspond to the contour level that I selected. So very useful. Of course, you can do many other computation once you've got this value. You can do whatever you wish by using Python or using other program or to which you exported your data. If I maybe if I write, if this is a data frame, so what if I write this one? Okay, this is a data frame PDF, which is I created with my columns X and Y. Instead of exporting toward Excel, I can just visualize the numbers by using, for instance, the F head, so just the first 5 lines of the path, and you will see your X, Y, and value. That can be useful. So, but there are many functions, very sophisticated functions that can do everything you can imagine. So, if you want to do something, some computation, particular computation of any type, go on internet, for instance, write matplotlib, and following matplotlib keyword, you'll write what you want. So I want to get some function doing something, some operation, and you will discover that there is already a specialized function that does exactly that without having to write code for that. Of course, you have to write code to use the function, so to prepare the data, as I told you this morning, and to further elaborate them. But for making sophisticated computation, everything is already defined. Questions, curiosity?
I have one.
Yeah?
Um, to me, it's the first time one course to get programmation,
Yeah?
and I want to know if there is a limit of such thing, because imagine you have a purpose, and the only limit is in or sorry, I
You
didn't
can
get
you
it.
can speak in Italian, there's no problem.
Okay, okay. Non avevo bene in testa cosa dire in inglese. Comunque la mia domanda era quale fosse il limite delle tecniche di programmazione, nel senso che il limite, da quello che mi pare di capire, è solo riguardo a quanto sei bravo a programmare o meno, giusto?
Certamente, perché qualsiasi altro programma che scarichi da internet dietro ha programmazione fatta, quindi qualsiasi applicazione che tu adoperi, che sia grafica, che sia di elaborazione, dietro le quinte usa un programma, no? Come facevo vedere prima su questo General Fits notebook, lo user finale, quello che vede è solo la funzione finale che fa i conti, ma quello che c'è dietro le quinte qualcun altro l'ha scritto ed è salvato in un file, no? Quindi qualsiasi cosa un programma applicativo faccia, dietro c'è sempre un programma, il che vuol dire che i limiti della programmazione non sono inferiori ai limiti di qualunque applicazione che puoi trovare su internet, no? Anzi, diciamo che se sai programmare, tu puoi andare oltre i limiti di un applicativo. Quindi puoi avere degli applicativi che sono stati concepiti per fare certe cose, tu invece vuoi estendere perché vuoi fare qualcosa in più rispetto a quelle cose. Se sai programmare lo sai fare, lo fai. Se altrimenti non sai programmare, devi dipendere sempre da quello che altri hanno deciso per te, no? E che può essere fastidioso in molti casi, no? Non solo, poi se usi un applicativo commerciale oppure comunque anche un applicativo libero, free, scaricato da internet, da qualcun altro, e difficilmente tu sai cosa c'è dietro le quinte. Tu lo adoperi, ci butti dentro dei numeri, tiri fuori dei risultati, ma non sai esattamente come questi vengano calcolati, i parametri che usano. Immagina che tu voglia cambiare dei parametri che vengono stabiliti di default dal tuo applicativo, ma non sai esattamente quali siano e non c'è nessun metodo per cui tu possa cambiarli dall'esterno, tu sei fregato, nel senso che o usi quei parametri oppure non fai altro. Se invece sai il programmare, ti scrivi gli algoritmi come vuoi tu, setti i parametri come vuoi tu e dai i metodi che servono per cambiare quei parametri. Quindi limiti non ce ne sono solo limiti, diciamo, dovuti alla capacità di programmare di ognuno. Più sai programmare, meglio è. E per
Ok,
farlo,
no,
ok.
sì, perché nel mio esempio, diciamo che conosco le tecniche chemiometriche che trattano ovviamente i dati, ma con delle regole abbastanza rigide e queste tecniche hanno dei limiti e quindi mi chiedevo ovviamente l'utilizzo di Python per analizzare i dati per superare i limiti che possono avere queste tecniche statistiche che comunque rimane, cioè, il problema rimane comunque al fatto che devi saper programmare
Devi saper
e
programmare, quindi devi,
trovare
devi dedicare del
sì,
tempo all'attività di programmazione, no? Uno può anche stabilirsi delle timetable, no? Tu dici, io un'ora al giorno la dedico a programmare, un'ora e mezzo, quello che è, no? E poi se ho dell'altro tempo libero e non so cosa fare, vado avanti. Non è mai tempo perso, non è mai tempo perso. All'inizio magari uno appunto tiene errori, non riesce ad andare avanti, eccetera, però mano a mano che provi, poi impari a programmare. Non conosco nessuno che, avendone avuto bisogno sul serio di imparare, abbia dovuto rinunciare perché non è proprio nelle mie corde. Non conosco nessuno, no? Chiunque si sia messo con un po' di sforzo è riuscito alla fine ad ottenere qualcosa, no? E non è mai tempo perso, perché appunto nel momento in cui tu programmi, e quindi scrivi un algoritmo e lo codifichi in un programma per fare le cose, tu capisci l'algoritmo stesso, no? Ci sono delle cose che magari sottovaluti o non ti vengono neanche in mente quando usi un applicativo scritto da un altro, no? Perché dici, ok, quando tu devi risolvere un problema in maniera algoritmica, tu devi conoscere ogni dettaglio di quell'algoritmo, perché altrimenti non sai scrivere un programma che lo risolva, no? Che lo implementi, se non conosci i dettagli, no? Ma qual è il ritorno? Beh, prima fai uno sforzo perché devi imparare l'algoritmo veramente, no? Quindi devi vedere tutte le variabili che concorrono nel definire un certo problema. E quindi passi del tempo, investi del tempo nello studiare l'algoritmo, ma quando l'hai scritto, e quindi quando l'hai scritto e funziona, allora tu sai veramente bene tutto su quel problema, no? Sai esattamente bene come fare a calcolarlo, no? Quindi quando vai a un congresso, discuti la tesi di dottorato, qualsiasi altra cosa, e ti fanno dal pubblico, ti fanno una domanda, dice sì, ma questa cosa come è calcolata? Tu parlo, sai benissimo come, perché l'hai calcolata tu, e quindi sai bene ogni passaggio che devi fare per arrivare lì, no? Se invece hai usato un applicativo, sai quante volte sento i congressi delle cose del genere? Questa cosa come è stata calcolata? Well, I don't know. That's the program to make this computation, but it's not very clear to me how it did that. Veramente ti fai una brutta figura e poi veramente è pericoloso, no? Perché magari stai trattando dei dati in una maniera impropria. Magari l'algoritmo è stato scritto per trattare una certa classe di dati e funziona per una certa classe di dati, ma non funziona più per dati diversi. Quindi che so, tu hai raccolto dei dati, supponiamo in temperatura, no? Per una certa grandezza, fino a una certa temperatura non troppo alta, diciamo so 500 Kelvin, no? E usi un metodo, un algoritmo che è stato calibrato per andare fino a 500 Kelvin. Poi tu però lo adoperi oltre 500 Kelvin e non ti rendi conto che l'algoritmo in quel caso lì non va, no? Non è stato calibrato, non funziona, no? E tutte queste cose sono un po' dietro le quinte dei vari applicativi e perciò anche quando adoperi un applicativo tu dovresti sempre chiederti su cosa è basato. Io conosco un sacco di gente che usa dei programmi a scatola chiusa, non sanno assolutamente cosa fanno quei programmi lì. E poi corrono in problemi perché li usano malamente, no? Li usano per situazioni per le quali quegli stessi applicativi non sono stati previsti, no? Sono delle estensioni che l'utilizzatore fa ehm, trattando i dati, diciamo, estende il range dei dati su cui va a lavorare senza sapere che cosa sta facendo. Poi si possono tirare fuori dei numeri, purtroppo questi programmi applicativi molte volte tirano fuori dei numeri, i numeri li tirano fuori lo stesso, bisogna vedere se hanno un senso o no. Nel momento in cui tu conosci l'algoritmo e sai applicarlo, sai implementarlo, tutte queste difficoltà le risolvi, impari delle cose, capisci bene le cose che fai e scrivi i programmi che facciano le cose che vuoi tu, non le cose che vogliono gli altri. Quindi nessun limite, grandi vantaggi, naturalmente bisogna investire del tempo nella propria formazione per arrivare poi a programmare. E all'inizio programmerai malamente, come dicevo, come ho fatto l'esempio questa mattina, scrivi un programma con una funzione dentro che è enorme, in cui ci metti dentro un sacco di roba. Perché sta funzione che ho scritto al mattino, che ho fatto vedere questa mattina, aveva così tanti argomenti? Questa qui, come mai, no? Perché mentre la scrivevo mi rendevo conto che avevo bisogno di fissare certi valori, di certi parametri, e quindi andavo a aumentare la lista degli argomenti alla funzione. Quindi dico, ah, ma un momento, a me serve un guess. E dove lo leggo questo guess? No? Ah, beh, glielo passo come argomento della funzione. Ah, beh, però a me serve anche un bound, voglio limitare i miei valori della variabile da raffinare, in quel caso era la Einstein Temperature, tra 10 e 2500 Kelvin. E da dove li prendo questi valori? Ah, glieli passo come parametro. Poi voglio fare un plot, il plot lo faccio su 100 punti, dove lo prendo su 100 punti? Gli passo ancora un altro parametro, no? Quindi quando il beginner, diciamo così, scrive la propria funzione, ma anch'io faccio così all'inizio, no? Guardi, scrivi la funzione e viene fuori alla fine una cosa enorme con un sacco di argomenti da passargli che insomma diventa poi illeggibile, no? Allora in questi casi uno si ferma, uno arriva alla fine, la prova, va dal capo che gli ha chiesto una certa cosa, gli fa vedere dei risultati, no? Dice ok, sono riuscito, sono andato in fondo. Il capo è contento, bla bla. Però poi uno deve tornare indietro, guardare la cosa che ha scritto, se vuole imparare veramente a programmare con una certa tecnica, guardare la cosa che ha scritto e dice come posso fare per migliorare il programma dal punto di vista della struttura, e allora comincia a vedere, questa funzione qui fa troppe cose contemporaneamente, quindi sarà bene spezzarla in più funzioni, ognuna con un compito specifico, e in questo modo vado anche a ridurre molto per ogni funzione quello che è il numero di parametri che questa accetta. Poi immagino di costruire classi, insomma tutto quello che ho spiegato prima che viene fuori poi passo passo, no? Però all'inizio uno scrive delle cose un po' così, no? Dopodiché però si raffina nel tempo e fa anche dei lavori, diciamo, che hanno un senso, che sono pubblicabili loro stessi, no? Quindi alla fine uno può anche scrivere dei programmi, può scrivere i suoi applicativi e poi pubblicarli, quindi altra gente userà i programmi scritti da te, insomma. Non ci vuole un tempo infinito per imparare, no? Uno dice, chissà quanti anni, no, insomma, se uno si mette un po' e dedica un po' di tempo, si arriva abbastanza rapidamente.
Ok, comunque tanta pratica.
Tanta pratica, sì.
Grazie.
Other points, other curiosity, problems?
Is it difficult to, let's say, translate from another language like MATLAB
No,
to
not at
Python?
all, not at all.
Okay.
Because the main advantage is you already know some other language. You already know how to program. You are already an algorithmical mind, frame of mind, and what it changes simply the syntax and the grammar of the new language. But the difficult thing is not the language, not the syntax. It is the structure of the program, and the structure is the same for every program. Python, with respect to, for instance, Fortran, supports much more structural coding. In Fortran, you also separate, you can separate the code in several subroutines and several functions and so on. But generally, people write very large subroutines that do a lot of things together and so on. The Python forces you or supports you a style of programming which is much more structured. So the code will be more readable and maintainable during the time. But if you know to program in Fortran or in MATLAB or something like that, with some exercise, you will move to Python.
No, I studied Fortran 77
Yeah.
during my bachelor, and at the time I could use it, but then I've never really used it, and so I don't really remember.
Okay, okay, yeah, yeah. Of course, you have to use. But if you already use MATLAB, okay, you have more or less the same thing. What is changed is just the grammar and the syntax, but the logic is exactly the same. So it is not difficult. It's like one guy that study Italian, English, and French has no problem to learning Spanish, for instance. So, because you have the frame of mind already required to learn a new language. Otherwise, it could be more difficult to learn a new language if you still have to learn the way of thinking, how to organize algorithmically a given procedure. But if you already know, that's no problem. In fact, in my life, I studied Fortran, basic, then Fortran. I learned Lisp in a couple of weeks, MATLAB and Octave in 1 week maybe. So I wrote also complicated program in MATLAB in nothing. And Python, I learned to use Python, the basic feature of Python, less than a week. Then I refined my knowledge. Now it's 2 years. I'm working on Python on since 20 years. It's just 2 years that I use Python. So it's very fast. Okay, now these files, I have other materials that I will load in the GitHub. That in a few days I will load everything. So you have the materials. Um, for your exercise, I also wrote this function, the logistic functions, for instance, just to see. I don't know if you know the logistic equation. It's a very simple equation of this type. X at the generation um, n plus 1. It is used by ecologists to study the evolution of populations. It is equal to k, a constant, times x, times 1 minus x at the time. Sorry, times x times 1 minus x. Okay. At the n is xn, 1 minus x. If you have the population of the nth generation, so the number of individual of one population, some generation, nth generation, you can compute the population at the another a successive generation, so the n plus 1 generation. And this k is just a constant that is related to the ability to replicate these generations, of this population. So the rate at which a generation grows, which is limited by this factor 1 minus xn, because as the population grows, resource for maintaining the population reduced. And so as the population grows, you can reach a limit where the population starts to decrease, maybe because the resources are diminishing. And so this is a famous problem, the logistic problem with this logistic function that you see there. And I wrote this little program to work with this problem. Now I want to show you some result. For instance, okay, let's use, I create a class which is called LGS, the LGS class. And for instance, if you want to see the evolution of the population, LGS dot plot. So I'm going to use this plotting method here for a k value which is 2.5, so just the default. And let's see what happened. Okay, you see what happened. I start from an initial value, our population, about don't put what I write, 0.1, and so I start to plot my the evolution of the population in time during 30 generations possible. You see that you have a growth of your population at the beginning then you have a small oscillation, then you arrive to a constant value. So the population arrives to an equilibrium value. I can also reduce the number of, so I can do that in plot, yes, here. So LGS plot, K is always 2.5, a neater number of generation I want to analyze, maybe just 10. So 1/3 is to first one, and you see this one, so very small oscillation, and then you arrive to a stable limit. If you increase the K, for instance, GS plot, I put K equal to 2.8. Let's see what happened. You see that you have more oscillations, but then you arrive to a stable limit. So after some time, you arrive to an equilibrium. So the population grow up to this value here, and then remain stationary. So the number of individual remains stationary. What happened to K equal to 3? So I increase the rate at which the population is able to replicate. Haha, you see that you don't reach any limit, any constant value, but the population continues to oscillate between two possible values. What happened at 3.5, for instance? You get this oscillation, which is could be more irregular. And so one can try to study not the evolution of the population, so the curve which the population followed during its evolution, but the number, the point over which your population oscillates. So you have in a case like this one, you have just one point. You arrive at an equilibrium point, and in this case, you have 2 points over which the population oscillates. Here you have probably more points, so you can compute a graph using the function plot, not the function LGS plot, but the function plot from k-mean, let's say 2.8 to, let's say 3.8, k-mean, k-max. Okay, 100 points, right? And see what comes out. Take some time. All right, this is the logistic plot that you see that when k reach a value which is close to 3, you have a bifurcation, so your population start to oscillate between two values. When k increase, you arrive at another bifurcation point, so you have oscillation between 4 possible values. Then each of these points bifurcate again until you reach this region here, which is a fractal. So every possible values is obtained between this value of the population level, and the exact value of the limit that you reach in each point here at each value of k will depend strictly from the precise value of k and the precise initial value of x, so the x0, the population at the initial time. So it is a fractal. It is a fractal because if you analyze a section here, for instance, the section from, let's say, 3.7 and 3.72, maybe, you see. You have this structure here, and you see that you have regions where, for instance, around 3.7, that the population start to oscillate between a small number of value, here 1, 2, 3, 4, 5, 6, 7, about. But then you, again, you finish in this random, almost random situation here, but it's not quite random because you see that there are regions where the points are much denser than the other ones. So who study evolution of population very often models this evolution by using the logistic equation. It's a very simple equation, very simple model that generate a fractal, so something which is very complicated from the at least from the numerical point of view, have a lot of interesting features. So I wrote this program to analyze this figure. If you go on internet and look for logistic equation, logistic evolution, you will see always a function, a graph like this one. So if you want to go deep on the problem, at least from the mathematical point of view, on the practical, etc., you can look for internet, and you have a program that allows you to reproduce the data that you see on literature by playing with uh, some number here, so with the value of k, number of iterations. So try to look, if you want, try to look to and to understand what this program does. It is not documented because I haven't not the time to write documentations. But you also have the interesting point for me here is this function, which is the logistic function, that the function that really compute the value of the logistic equation. And I use this function that do not return a number, but instead of using the keyword return, use the keyword yield. And the keyword yield do not return a number, but returns an iterator, a generator for getting this number. And it can save some space in memory of a computer. I have, for instance, 5,000 iteration over the population to reach the convergence, or anyway, to reach the point like this one. So I want to be sure to have reached in a situation that allows me to compute stable values or values that exist in this fractal region, 500 iteration. But then I will analyze only 100 of the last value of the population I got. So I know that it is not clear. Anyway, imagine that you have a number 1, 2, 3, 4, 5, 6, 7, and so on, iteration. And then to make this plot, I will look not at all the value of the population I got through all the possible iteration, but only the last one. So fire this one, and so on and so on. And so on, up to 5,000 in this case. So your memory of computer must store, to make this computation, 5,000 values. And maybe that in some cases you have to use much more iterations. So maybe 20,000, 100,000, 1 million. So you have a very large list. And on this list, you will always consider 100 values, which are the last 100 values of this list. All the other numbers are discarded. So that's a waste for memory for your computer. So instead of generating a full list and then analyze the list, by this, I could do that by using here a return. If I use a return, then the logistic function will return the 500 elements list. Instead of getting this large list, I put here yield here and no return, and I get a generator for the list, not the list itself. So when the interpreter works, it does not compute nothing. It does not compute a list, but provide me a generators, and I can use this generator in a for loop like this one. This for loop goes from a variable that it is written with an underscore. It means that I'm not interested in defining a name for that variable, just a loop of some numbers. And I will do this loop for 4,900 iteration. And for each iteration, I use the generator IX, which is called XList generator. And simply, as I showed you in some lecture, I can use the next function to get the value of the element generated by the generator. And I simply throw it away. I don't want to store. I don't need it. So I simply delete it. And so I run this next function for 4,900 times without storing anything. That save memory. Then for the last number that I want, for the last position, so the last 100 position, I store effectively my value of the generation in a list. So instead of a 500 list, 5,000 lang list saved in my computer, I just have a 100 elements list, which is much more take not so much space in the memory of the computer. So that's the logic of this logistic function, logic of the logistics. Sorry for the words. So and by using this YEL, so I wrote this program just for showing an example of the usage of YEL that can save you some memory. There are just subtle and sophisticated usage of Python. Um, if you want, if you study this program and you want to modify it, there is a room here for a problem like this one to use recursion. So because the logistic function, you can also imagine a logistic function that call itself for each computation of the generation at the next level. And so you can rewrite this logistic function by using recursion. That's an exercise for you. So study the logic that is inside this program, and then you can try to modify in some ways, of course, the result, the correct result, that you have to use as a check to compare these results here. So if you want, you can make exercise, and then you can also send me your exercise. Send me your problems, your trial, the error you got, asking help. So the idea is that I'm not flying away. I'm just in my office for, I hope, for many times, and so for much more time again. Um, and so you during time, not tomorrow, not next week, but maybe when you want, when you have time, you have problems and you want to learn really you make some practice in programming in Python, you can always ask out to me for several points, and I will be glad to help you to build and to construct something with you. Okay, question. This was supposed to be some question time, so if you have other curiosity. Another exercise is sorting. Okay, can close some of this. I have this sorting notebook. This is a notebook showing the usage of code, sort code, that implement, I think, so many, just say, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9 way of sorting a data set. So I imagine what I can do to sort numbers in a list, and how many ways I can do it, and how much they are effective, how much they are performant. And so I wrote this code that do the works and implement all these methods. That was supposed to be an exercise for you during this course, but I have no the time to go through it. Anyway, you can consider it. I have a class, my sort class, and all the functions which are implemented within the class. And then I test it on some data set made of random number in some range. And you see that I have what you have written here is just the time of execution of each data set. You have a data set of sites 300, so you have 300 numbers. And then the data set is They are random numbered, not ordered data set. Um, you can produce for a not ordered data set, you can produce an ordered data set, and then you can scramble it in some way. So destroy the ordering, but in a limited way, and test so all your method with this different data set. So a totally unordered data set, a totally ordered data set, and intermediate disorder data set that I create by using classes which are written in this data class BI here. And you see, for instance, that this method, which I call SS, perform very badly. This is the time of the execution time in milliseconds. And this takes more than 1 second. It's about 1.6, 1.7 seconds to execute over the totally disordered data set. If the data set happened to be ordered anyway, totally ordered, well, it takes only 0.14 second to perform. You have to compare all these numbers with this NP. This NP is a NumPy function to perform in the sort, and it is much, much faster than all the other possible methods I implemented because it contains code which was compiled and optimized, so it works very fast. But in all the other cases are all the possible um, function that I implemented without any optimization. So you see, for instance, that this data set, this method on the data set which is totally ordered, perform very badly if the data set is totally disordered. But in case it is totally ordered, it compares with the timing order method, which are much faster than this one when the data set is totally disordered. So we have this MS. It takes only 51 milliseconds compared to 1,600 milliseconds for the SS method. But then when the data set is totally ordered, it takes the same time. Another case, for instance, this DBC double cycle, this is exactly equal to the sorting function that we saw in the lectures in an exercise. You see that this performs fairly well in case of the total disordered data set, 22 milliseconds instead of 1000 so on compared to this one. But when you go to datasets which are partially ordered or totally ordered, this perform not very well. So 13 milliseconds with respect to 0.14 in case of this SS method. And for instance, the dataset SW3 that contain 80 switch in the dataset. So this is not totally ordered. This work in 5 milliseconds, and this work in 13 milliseconds. So it performs worse than this one, and so for the other method. Then I also implemented the smart data set, the smart method, not smart data set, which make an analysis, preliminary analysis of the total data set, the original data set, and decide if it is better to use an algorithm or another algorithm. So smart start by making a test on a small portion of your data set, so not all 300 numbers, could be many more elements in your data set, could be 1,000, 5,000 elements in your data set. And then smart perform an analysis on a small fraction of the total data set and decide which method is best for sorting the full data set. And so the smart method here works well because always is produce your result, your final result with the smaller time possible compared to the other possibility. Of course, it's much more slow than the NP sort function, but anyway, it performs quite well. So if you go in this to look at this code, you will understand how did it, and that's all. So the statistic function which exists in this Jupyter notebook makes all these tests. So, if there are no questions, I will officially close this course. As I probably some of you seen, I this morning or some couple of hours ago, I sent you an email for if you need for a certificate of attendance, write me a mail by writing the subject certificate or something like that, capital letters, so that I will recognize immediately the mail, the request, and I will prepare a PDF certificating that you attended this course. As I wrote in the mail, this could take some time because I will sign this certificate, but this certificate must be also be signed by the coordinator of the PhD school. It is always engaged in many things, so I don't think he will sign immediately. Um, I will await some time to get all the mail from you, all the requests from you. So I will prepare a batch of PDF file to be signed by this guy, and then I will send back to you. Questions? Well, if there are no questions, I will close here. So interrupt the sharing of this file, and I hope that you have learned something